Welcome to Fun Facts Online. Today we are going to dismantle one of the most successful theories in the history of physics. We are going to look at why the concept of a particle, the fundamental Lego block of our universe, is dissolving before our eyes, and what is coming to replace it. For nearly a century, our understanding of metals, semiconductors and insulators has been governed by what we call the standard model of condensed matter physics. This model rests on a granular view of reality. It assumes that matter is composed of discrete actors. We usually call these electrons. However, in the crowded, noisy environment of a solid crystal, describing them as naked electrons isn't quite right. Instead, physicists describe them as quasiparticles. These are the dressed actors of the quantum stage. Imagine an electron moving through a solid, but it is surrounded by a cloud of excitations, dragging the local environment with it. It moves with a renormalized mass, meaning it acts heavier than a bare electron, but it still carries a well-defined charge and obeys the polite statistics of the Fermi-Dirac distribution. This framework is known as Landau's Fermi liquid theory. It is, without exaggeration, one of the greatest intellectual achievements of the 20th century. Lev Landau, the Soviet physicist whose insights defined much of modern theoretical physics, proposed this radical idea in the 1950s. He argued that even when interactions between electrons are incredibly strong, we can still mathematically map the system one-to-one onto a system of non-interacting particles. Think of it this way. Imagine a crowded room of people trying to cross from one side to the other. If they are polite and don't touch each other, they are like a free electron gas. But if they are pushing, shoving, and holding hands, that is a strongly interacting system. Landau's brilliance was realizing that you can still describe a single person's motion across that crowded room, provided you account for the drag of the crowd. That person effectively becomes heavier and moves slower, but they remain a distinct entity. You can track them. This is the quasiparticle. In a Fermi liquid, these quasiparticles exist near a specific energy boundary called the Fermi surface. This is a distinct contour in momentum space that separates occupied electron states from empty ones. The existence of this sharp surface is the hallmark of a metal. It ensures that excitations are long-lived. If you kick a quasiparticle, it rings like a bell. It retains its energy and momentum long enough to be detected. This theory explains why your computer works. It explains why copper conducts electricity and why glass does not. It has been almost too successful, predicting the heat capacity and conductivity of gold, silver, aluminum, and silicon with astonishing precision. It cemented the idea that matter consists of particles into the bedrock of our intuition. But intuition is a fragile thing in the quantum realm. In the dark corners of the quantum material universe, the quasiparticle is dying. We are seeing this in cuprate superconductors that conduct electricity without resistance at relatively high temperatures. We see it in the twisted atomic sheets of magic angle graphene. We see it in materials known as strange metals. Experiments in these systems reveal a state of matter where the concept of a discrete particle breaks down entirely. The electrons are so strongly entangled, so fiercely interacting, that they lose their individual identity. You cannot pull one out and say, here is an electron. If you strike the system, the energy does not propagate like a billiard ball. It dissipates into a collective, viscous hydrodynamics of quantum information. The particle has dissolved into a particleless soup. This breakdown began to show its face in the late 1980s. When physicists heated copper oxide superconductors above their critical temperature, they entered a normal metallic state. But this metal was anything but normal. In a standard metal, electrical resistance arises from quasiparticles colliding with impurities or vibrations. At very low temperatures, this resistance is proportional to the square of the temperature. This is a direct prediction of Fermi liquid theory, but in the cuprates the resistance scaled linearly with temperature. It was a simple straight line, extending over hundreds of degrees. This behavior, dubbed strange metallicity, was a direct violation of the rules. It implied that the scattering rate of the charge carriers was not determined by the material's details, but by the fundamental limits of quantum mechanics itself. This is known as the Planckian dissipation limit. It is the fastest possible rate at which energy can dissipate in a quantum system. It suggests the system is maximizing chaos. But here is the catch, and this is the central paradox. For a system to scramble information that fast, it cannot be composed of long-lived quasiparticles. If particles existed, they would take time to collide, time to scatter, and time to travel. A Planckian dissipation rate implies that the mean free path of the excitation, the distance it travels between collisions, is shorter than the wavelength of the particle itself. This is a physical impossibility in the classical sense. A wave cannot scatter before it has oscillated even once. A particle cannot crash before it exists. The only conclusion is that there are no particles in a strange metal. The electron fluid has lost its granularity. It acts more like a soup of quantum entanglement, a quantum slush where charge and energy are transported not by individual carriers, but by collective, many-body excitations that have no classical analog. So if we cannot describe matter by listing its constituents, how do we describe it? We describe it by its shape. We are entering the age of the particleless state, where the fundamental currency of physics is not the thing, but the not. This brings us to the realm of topology. Topology is the branch of mathematics concerned with properties that are preserved under continuous deformations. A coffee mug is topologically equivalent to a donut because one can be smoothly stretched into the other. Both have one hole. A sphere is distinct because it has 0 holes. In condensed matter physics, topology has moved from a mathematical curiosity to a central pillar. Physicists realized that the quantum wave functions of electrons can wrap around the abstract space of momentum in knotted configurations. In a Fermi liquid, this topology is trivial, an unknotted sheet. But in these new phases of matter, the wave function acquires a twist, a topological invariant, often called the Chern number. This is relevant because topology offers a way to have structure without particles. In a topologically ordered state, the fundamental excitations are not electrons. They are fractionalized entities. Consider the fractional quantum Hall effect. Here, electrons are confined to 2 dimensions in a strong magnetic field. The interactions are so intense that the electrons dissolve and form a new incompressible liquid. The excitations in this liquid carry a fraction of an electron charge, like 1/3 of a charge. These are not simply thirds of an electron floating around. You cannot cut an electron in thirds. Rather, they are topological defects in the quantum fabric, vortices in the entanglement fluid. We call them anyons. They are neither bosons nor fermions. When you braid them around each other, they retain a memory of the path, encoding information non-locally. This was our first glimpse of the particleless regime, a state where the particles are emergent phenomena, arising from the collective topology of the system, completely distinct from the underlying electrons. The most dramatic manifestation of this post-particle world is the quantum spin liquid. In a normal magnet, electron spins align in a rigid pattern, like up, down. This is static order. But in a quantum spin liquid, the spins never freeze. Even at absolute 0 temperature, they continue to fluctuate in a highly entangled quantum superposition. They are a liquid of magnetic spins. If you try to flip a spin in a normal magnet, you create a wave. But in a spin liquid, the electron's spin breaks apart. The electron, which is usually a composite of charge and spin, undergoes fractionalization. It splits into a spinin, carrying spin but no charge, and a chargon, carrying charge but no spin. This separation is forbidden in the vacuum of free space. But inside the topological matrix of a spin liquid, it is allowed. The spinin is a ghost, a topological knot in the spin field. Recent experiments in materials like ruthenium chloride have shown hints of these fractionalized states, suggesting the presence of neutral, heat-carrying fermions. Here, the topology of the ground state dictates the physics. The atoms and electrons recede into the background, acting merely as the substrate for these emergent dancers. Now, we arrive at perhaps the most mind-bending development in this field. It comes from an unexpected source: string theory and black holes. As condensed matter physicists struggled to describe the strange metal soup, high-energy theorists were developing the ADS-CFT correspondence. This theory suggests a mathematical duality between a quantum field theory in a lower dimension and a theory of gravity with a black hole in a higher dimension. Roughly speaking, the surface of a higher dimensional universe can behave mathematically exactly like a quantum soup of particles. When physicists applied this duality to strange metals, they found a startling connection. The mathematical description of a particleless quantum critical state is dual to the physics of a black hole horizon. Why? Because black holes are the ultimate scramblers of information. If you throw a book into a black hole, the information is scrambled as fast as theoretically possible, at the Planckian limit. Recall that this is exactly what happens in a strange metal. This has led to the holographic duality approach. In this view, the strange metal does not contain quasiparticles because its dual gravitational description is a black hole, which has no particles in the traditional sense, only a smooth horizon and space-time geometry. The electrical resistivity of a strange metal can effectively be calculated by solving Einstein's equations of gravity in a higher dimension. The viscosity of the electron fluid relates to the absorption of gravitons by the black hole. This convergence, where a tabletop sample of cuprate superconductor is mathematically equivalent to a black hole, implies that the particleless state is a fundamental universal state of quantum matter characterized by maximal entanglement and minimal structure. To ground these lofty ideas, physicists needed a toy model that could be solved. This arrived in the form of the SYK model, named after Sakdev, Ye, and Kitaev. It describes a cluster of fermions interacting with infinite range and random couplings. It is a zero-dimensional quantum dot of chaos. Crucially, the SYK model is a non-Fermi liquid. It has no quasiparticles, exhibits Planckian dissipation, and has a holographic dual equivalent to a 2D black hole. The SYK model has become the harmonic oscillator of the particleless age. It proves that one can have a rigorous mathematical theory of matter without quasiparticles. It shows that when you remove the particle, you are left with symmetries usually found in gravity. We are discovering that particles are perhaps just a low-temperature, weak interaction approximation of a much deeper, more entangled reality. So, what are the implications of this new era? First, high-temperature superconductivity. The holy grail of materials science is a room-temperature superconductor. It is widely believed that the secret lies in the strange metal phase. If we understand how the particleless soup condenses into a superconductor, we might be able to engineer materials that remain superconducting at ambient temperatures. The topology of the wave function is likely the key to locking this state in place. Second, topological quantum computing. The anyons of the fractional quantum Hall effect are the basis for this technology. Because these states depend on global knots rather than local particles, they are immune to local noise. You can shake the table, and the knot remains a knot. This topological protection is our best hope for building a quantum computer that doesn't crash from decoherence. Major tech giants are betting heavily on these particleless excitations, known as Majorana zero modes, to build the future of computing. And third, a new universal hydrodynamics. We are moving toward a description of electron flow that looks more like fluid dynamics than electronics. In clean samples of graphene, electrons flow like water. They form vortices. Understanding this viscous particleless flow could lead to ultra-low power electronics that utilize the collective motion of the fluid rather than pushing individual, resistant particles. For centuries, reductionism has been the engine of science. We broke things down to atoms, protons, quarks, and electrons, assuming that if we understood the brick, we understood the house. The particleless state teaches us that this is not always true. In the regime of strong quantum entanglement, the brick ceases to exist. The system behaves as a single, unified, topological entity. The electron is not a little ball, it is a thread in a tapestry, and when you pull it, the whole fabric moves. Topology beyond the Fermi liquid theory is the map of this new territory. It tells us that the universe is not just a collection of marbles, but a dynamic ocean of quantum information, structured by knots, links, and geometry. As we venture deeper into this strange world, we are finding that the breakdown of the old rules is not a dead end. It is a doorway to a deeper, more beautiful, and profoundly interconnected reality. The particle is dead. Long live the topology.